Thank you for this nice introduction and the invitation. So as the talk title suggests, it's going to be very different from what probably you have been listening to. I'll try to, so the focus of the talk is what's the problem and what's the difficulty, and what the challenges in that problem, and how recently we have been able to overcome the difficulty in solving this problem. So the problem that I'm going to look at today is, so we have a controlled diffusion. So this is the controlled diffusion, so that's the drift component. It has a control parameter, so that's denoted by ZT. And then I have a diffusion component, which is associated with the Brownian motions, and a jump component. So this will be a Poisson process and with a finite characteristic measure. Okay, so these are some standard. I'm not going to explicitly write what are the assumptions. Something that's very standard in control theory. So you take B to be local ellipses with some growth assumption so that the solution exists, and sigma will be also local ellipses, and G will be local ellipses up to some integration criteria. I would require this to be locally non-degenerate, and as I said, the Poisson process has finite mass, the characteristic measure of the Poisson process. Okay, now what also I have a function C which is non-negative and continuous function, and here U is a compact metric space, and my control is going to take value in this compact metric space. And this U, calligraphic U, it's a set of all admissible control, whatever it means. And the idea is to minimize, or that's my cost function. You can see that's a long time average of an exponential cost. Okay, so that's my cost function, and the problem I'm interested in to find out this lambda star, which is the optimal value of this cost. I mean, that's the problem. Might look complicated, but this is the problem. So the questions are pretty standard, what generally asked in this scenario. Can I find an existence of optimal Markov control for which this value is attained? And if there exists a Markov control, how to characterize such Markov control? How do I find them? And so these problems are generally related to what is called the eigenvalue problem. So this is the generator corresponding to the jump diffusion, and so that's the operator. And then you have this eigenvalue problem. You see this lambda star serve as an eigenvalue for this operator. So of course, then one would be interested whether such operator has equation has the existence of solution or not, and whether such solution is unique or not. Now, it might look a fancy question that why, I mean, you took a control jump diffusions and you started asking some sort of questions, why you are even interested in such questions even? Well, so even to understand the question, it all starts with, even if we don't want to consider the control, we can start with a very classical question that I don't have a control, I have a process run by the diffusion or any Markov process you like, and I would like to understand what happens to this quantity. Its limits tends to infinity. Okay, so this can be also seen as the Laplace transformations of the occupation measure. So that's something is related to the large deviation, or the study of the large deviation. But that's the quantity that I had, but I also had a control parameter here. So this question is also something related with the large deviation problem. Now, if things are very nice, in other words, if I have a semigroup, okay, so which is, so semigroup acting on some function f that looks like 0 to t c of xt dt f of x capital T. So that's a semigroup, Schrodinger semigroup. if you look at the semigroup, and if this semigroup has some nice property, if these are compact semigroup, then one expect, so the norm of this semigroup is exactly this one, which is this one. And then if you take log and take 1 over t, this is expected to go to the principal eigenvalue of the semigroup. Okay, so then you see the connection that this quantity is, let me write it small lambda star, why it has to be an eigenvalue. So that's the motivation, I mean, or some heuristic behind this. But I said something about that this semigroup is not any semigroup, it has to have some compactness property so that this limit exists. The trouble with this is the one I'm going to consider here, even if you drop this term, the diffusion process, whatever semigroup it generates, is not going to be compact. So then how different is the story when I have a non-compact situation like this, okay? So I'm going to come a little on that, and okay, I'll say something when I come to it. So what is the difficulty? So to understand the difficulty, let's look at a situation when the characteristic measure, so this is the characteristic measure for the Poisson process is 0. So that means I don't have any jump component, I'm just purely looking at the diffusion process. There is no non-local interaction, and this is the corresponding, so I don't have this component. So then if I put that 0, so whatever is left here, even if you want, you can drop this minimum, you just think there is no u, or this u is singleton. So you have a linear operator, okay, and you ask the same questions, what happens to this guy? I don't have a control, x is my diffusion, what happens to this guy when I'm looking at a non-compact situation, okay? So if it goes to the limit, okay, is this limit eigenvalue, okay? And in this situation, as I said, this is going to be a principal eigenvalue, then what is the meaning of this principal eigenvalue? So those are some difficult question, actually it remained open for a long, long time. It got solved 2015. So this is something happens. So the strategy is the following. So the strategy of whatever is mentioned here is the following. First of all, how do I prove this operator L, whatever I have written here, whether you put the infimum or a minimum or you don't put the minimum. So you have operator L, which is the generator of the diffusion. And I want to know what happens. When can I say that I have a solution, or at least I have an eigenvalue for this guy in whole dimension, whole domain, and size positive? So that's the question. When can I say that? Now the strategy to do this, at least the way one can prove this, you start with the Dirichlet problem. You look at the problem in a ball of radius 0, and where it is known that this problem has solution, okay? So this sign would be positive in Bn 0, okay? And there is, and I also want my sign to be 0 on the boundary. So that's the Dirichlet eigenvalue problem. So this problem on general domain was fully characterized all possible properties of such problems by a seminal work of Berestitsky, Nirenberg, and Varadan. So this is one of the classic in eigenvalue problem. So they did a lot of analysis for this kind of operators with a rough boundary. But so you first solve it for the bounded domain, and then you let the domain go to Rn. So now you increase the domain to go to Rd, and somehow this happens that this will go to some value lambda. One can prove it is monotone with respect to domain. The more you increase the domain, that lambda n starts to increase. So it's a scalar, so it will have a limit, okay? And it could be infinity also, okay? Depending on that C I have, okay? Let's see if it's finite. And also, this will go to some psi, okay? So this part is also, it's not really question in this situation, but it will be question in our situation. Suppose this psi n goes to psi in whatever sense, whether it's all with all derivatives or let's say in C2, okay? Locally, it goes to psi. So you pass to the limit to this guy and you get an eigenvalue, okay? Very nice, I get an eigenvalue. Now, the problem here is the following. Now, when we are looking at the Dirichlet problem, it is known there exists only one lambda or lambda n and psi n with such property where psi n is positive, and this equation is solved. There is one lambda n, one psi n. You cannot have several pairs. Now I have proved only one existence. It does not say how about the uniqueness. Can I say this is the only pair I have, which is the case when you have a compact semigroup, by the way. Okay? But now the same question arrives here. Is it the only pair where my psi is positive and lambda psi solves this thing? And I find it's quite remarkable. But after seeing the proof, it doesn't look that remarkable. But they proved it. They proved that if you take this lambda, which is obtained as the limit of this guy, okay, any beta above this lambda, this equation has a solution. You can find a psi beta such that, so there exists psi beta, so that L psi beta equal to beta psi beta, and where psi beta is positive. So this is a big problem. It creates a lot of difficulty in understanding the problem I started with. Characterization is a big trouble here. Now I have a uncountable many values, it's a whole spectrum, continuum, and you start getting a lot of eigenvalues. Okay? Of course, the question is still valid, whether should I call this as the principal eigenvalue because this is the smallest one. And they said, yeah, let's call that as a principal eigenvalue. And they gave certain characterization to justify when it's a principal eigenvalue. Okay? So this is somewhat heuristic what happens even when you have the don't have the non-local interaction. Okay. So that's the one. So though I started problem during my PhD days when I first, I did it the same approach to get one eigenvalue, which was somehow enough for my purpose. So we did this work in 2017, it came in 2019 with Shubhamay and Ari. So Shubhamay is probably going to talk more about the local version of this. When we exploited many phenomena in an unbounded situation and got a relation of this process with something called Dupes transformation or twisted process. So you can twist the process, change the drift, you get a twisted diffusion, and the property, the recurrence property of the twisted diffusion has many things to do with simplicity, whether this eigenspace is one dimension or not, or monotonicity property of the eigenvalues, and there are a lot of equivalent criteria. And one of the surprising thing which came another work with Ari and Devdeep, so it says that something in criticality theory, it's known as minimal growth and infinity. It's called Agman's criteria, which is pretty popular in PD community in potential theory. This property we found to be equivalent to what we call the right monotonicity of this lambda. So what happened here is, so suppose I have two potentials, C1 less than equal to C2, but they're not equal. Then the principal eigenvalue in bounded domain, by the way, in bounded domain, the principal eigenvalue corresponding to this, so D is for Dirichlet, is strictly less than C2. So this is something happens when you're looking at the problem in the bounded domain. This property is lost in unbounded domain. You can have two potentials. They are, one is above another one in a set of an open ball, let's say. Still the eigenvalues are same. And this creates a lot of difficulty in the analysis. So the question is when this has monotonicity property. So that's also important question. And this monotonicity property is also related with the fact that whether this psi has, is one dimensional. So if you look at the principal eigenvalue and all the principal eigenfunctions, you want to know whether the vector space is one dimension or not. It's a classical matrix theory question. What is the dimension of the geometric multiplicity of lambda? So we want to prove it's one. And we proved that this question is related to the monotonicity of lambda. And this is, and we proved actually the twisted process, recurrence of the twisted process is equivalent to what is called the minimal growth at infinity, which is very classical in potential theory. But yeah, so that's probably you might say. Okay. Now, so Exactly, so this is what I did here. So you solve the problem in bounded domain, pass to the limit, you get a pair, and you call this lambda as a principal eigenvalue, a generalized. Why it's generalized, it goes back to these people, Varadan, Birestiski, Nierenbach, and Varadan. Yes.
You start with a ball and the ball.
Yes.
Is anything special about the ball?
No, you can take any domain, that just increase, yeah. Yeah. Okay. Now, see, so far, this lambda has nothing to do with this exponential cost I have considered there. I just found one lambda by this increasing this ball, but finally I have to answer the question whether this lambda I have got is the same as the exponential cost I had. Okay, so it's not, in general, this is true actually. Okay, this used to be, I mean, there was a belief that they are equal, but then we found counterexample that it is not true. In general, you have, this inequality could be strict. So this is something that I have corresponding to the exponential cost I had, and that's I got from the limiting process. So under certain reasonably nice assumption, we prove that for some nice class they are equal, which is the purpose, but that's for the local case. Okay, and as I said that this is came the interesting paper of Birestiski and Rossi in 2015, where they first studied the eigenvalue problem in unbounded domains, in particular RD. Okay, and as I just mentioned, so in this work, we did something with the monotonicity property of this lambda with respect to the potential, which is C. So if C increases, decreases, whether my lambda is strictly increasing or decreasing. And as I said, there are a counter example. It did not hold. So when it holds, what is the special feature that we get? So that was the topic of this work. And okay, so this is another, so this is one I got from the limiting process. Now, as Sandeep also pointed out, if I take different domains, do I get different limits? It's not, because there is a monotonicity in the domain. You get the same limit. And you also have this characterizations. So you forget about this space. You think this is nice C2 functions, but you have this characterization that the principal eigenvalue can be characterized like this, okay? You take all the super solutions. So the lambda that I get from the limiting process is exactly this lambda star F. So here, the F is the potential. So you vary F. So in my case, it is C, the cost. But for linear operator, I've just written it like F. Okay, and something that I had mentioned, that if you take any lambda that lies above lambda star, you always have a solution to this guy. Okay? Okay. And one of the tool that we developed in this work is this guy, which is called the stochastic representation of the principal eigenfunction. So psi star is the eigenfunction that is corresponding to this lambda star, and we call it a stochastic representation. Okay? So you start from anywhere outside the ball. So you take any ball, fix any ball of radius r we have taken, and you start the process and wait until the process hits the ball, okay? And if this won't be true in general, okay? Because this guy could be, could have this exponential moment of u to the power of this hitting time could be infinity, because it's not guaranteed. But if this representation holds, then something interesting happens. This is called the stochastic representation of psi, okay? And it's equivalent to many other things. One of the thing is the minimal growth of infinity, that's of psi star, okay? Okay, so this is something that's everything that I was trying to say happens in local case, okay? Now come back to the non-local case. Now I want to do the same thing. Let's say, okay, now I have a way to do solve this problem. Now I add the non-local interaction, and I said, okay, I know how to do it, so can we do it? First hurdle, nothing is known if I have this, instead of this, which I is my non-local operator, so I had that non-local term. So I is actually L plus this non-local term, okay, of psi n. It's not known that whether this guy has a solution. Even if you take bounded domain, if you want to study the non-local problem, is Dirichlet eigenvalue problem, it has not been done so far. That was the first thing where we stopped, because it was not done. And there are some cases which have been done, but it doesn't fall in the kind of problem we are looking at, because we are looking at something with the rough kernel, because we don't have any assumptions about the density of the characteristic measure. So that's where we stopped, and we had to spend some time to prove. It was not really a big hurdle, but somehow one could manage to prove for any nice domain, this problem has a solution, okay? And very nice solutions, actually. So this is something that you could prove. You can think these are all C2 functions. So you can find a pair, okay, that solves the eigenvalue problem, which is 0 in the complement, because we are looking at the non-local interaction. So I have to specify the value in all of the complement, not only on the boundary. And it has to be positive, and you can normalize it to 1 at some point so that it's unique, okay? So this required to make this guy unique. So you get a unique pair. It's not a big thing, but one can prove this with some effort, okay? And you also have the one I said is the domain monotonicity property. If you increase the domain, the eigenvalue strictly increases. So all the thing that we have seen for local cases, when we don't have also with the potential. So if you increase the potential on a set of positive Lebesgue measure, the eigenvalue strictly increases. So something that one expect looking at the local case, that this is something should hold, and it holds, and it also has something also, it's also true in local case, is this convexity property. If I take two potential and take their convex combinations, so this eigenvalue is a convex function, okay? So this is something one can prove, so not a big thing, but it requires a little bit of work. So now I have, so first hurdle is solved. So now I can solve this problem in bounded domain. So that part is not a big problem. Let me say, if I just, again, I start with the problem in Bn0. I is my non-local operator. Let's say phi n is equal to, let me still denote it by this, in Bn0. This is what I do. Phi n is positive in Bn0, and it vanishes, and phi n is 0 in Bn complement, in the whole complement. This is an IC2 functions inside and continuous all of RD. So that has a solutions. Now what we want to do, I want to increase the domain, right? So, and as I said that this thing increases because of the domain monotonicity property. As you increase the balls, so this is increasing, strictly increasing, it goes somewhere. Let's say it's finite, okay? Making everything nice, live. So it goes to some lambda star, okay? Now I want to pass the limit here, if it can be passed. So this is something I didn't mention specifically, how one pass this limit. We are talking about functions, and then we are taking limit of functions, okay? So the classical theorem in analysis says, oh, we need to have Haskell-Ardsley, some sort of Haskell-Ardsley, then I can pass the limit. Now, do we have Haskell-Ardsley for this class of functions? First question, how do I know? Okay, for local case, this was tackled by one of the fundamental inequality in PD. It's called Harnack's inequality, and potential theories knows this thing. They also have been proving such stuff. Harnack's inequality. What Harnack inequality says is that if you are looking at the local case, you look at this domain, okay? You pick a point, any point, and fix a value here. So which I had done in the local case, by the way, this to be 1, right? Which I had done. Then the Harnack inequality says if you take any compact set inside, okay, then the value of the solution in the compact set is bounded above by a constant. If you fix a value, it controls the value in any compact set. That's the Harnack inequality. So one point controls the value in a neighborhood of that point or any compact set around that point, okay? And this constant only depends on the coefficient of this PD. It does not depend on the solution. That's crucial. It does not depend on the solution. It depends only the coefficient I had A, B, C, drift, diffusion, and the cost. It doesn't depend on anything. So if I have a family of psi n, they are uniformly bounded on a compact set, just because if I fix at a value. And therefore then there are some standard regularity estimate of PD that can be used to prove that the function has, they are equicontinuous, the derivative is equicontinuous, and double derivative is equicontinuous, you pass the limit. So you get this largely. So this is the crucial thing, that I need to have Harnack property. Bingo, Harnack property fails for this case. You cannot have Harnack when you have rough kernel non-local. There are counterexample that says Harnack does not work. How do you pass the limit? So it was a challenge for us also. For quite some time, we were wondering what to do. Whether, how do I know even, so we can normalize all of them to have supremum norm 1, but then as you let n tends to infinity, they very well go to 0. The supremum can go to run away to infinity. So on compact set, they might go to 0. We really don't know. So this was the hurdle, and we identified two class of problems which are of importance, in which case we can pass this limit. We cannot apply Harnack because that's out of question, because there are counterexample Harnack does not hold. So we have to bypass it using something else. Okay. This is something one could do. Okay, before I go there, let me mention one could also, so this development that we did for Dirichlet eigenvalue problem in bounded domain is also corresponding to something called exit time problem. Okay, so if you look at the Dirichlet problem in bounded domain, okay, and you want to study this exit time problem or exit rate problem, it is known as. Okay, so it is the probability that the process will stay at least t amount of time in the domain, and you want to find the rate of exit. So this theta actually, it's correspond to some eigenvalue. So this is the theorem one could prove just from the properties that we have developed for the eigenvalue in bounded domains. So if you can solve this eigenvalue problem, and you can show this principal eigenvalue is exactly the exit rate, and any minimizing selector of this equation would be the optimal Markov control, and any optimal Markov control will be the minimizing selector of this guy. So it's a full characterization for this exit rate problem in bounded domain. Okay, that comes as a consequence of these properties of eigenvalues. Okay, and this is what I was saying, that the passes of this limit, if I increase the domain, because we don't have Harnack, it doesn't hold. We don't know, because there are counterexamples for which Harnack does not hold. So Harnack, the tool, we don't have. So now this is something is generally used for the stability property, but this also helps us here. We didn't use the stability, but what we used, which is called the barrier function. So to construct something we call a barrier function, and this is, I think it's interesting. Something I also find it new. So because there is nothing known in eigenvalue problem in non-local case. So this is, so suppose we have this Lyapunov type stability condition. So we have a Lyapunov function. So this is known as the Lyapunov stability conditions, or geometric ergodicity conditions. Okay, so we have a function, and this v, this function, you can think that v grows at infinity. It's a Lyapunov functions, and then I also have an L. And L should grow faster than C. So there's a condition like that. Okay, and to justify the non-local term here, I also need this to be locally bounded. Okay, so this is assumption, and there are several examples for which this holds. So the big thing. Now, this is most of the time this is used to have stability for the Markov diffusions or the Markov controls. But it serves an extra purpose here actually. That's what is I find interesting. So this is what happens. So you start with the eigenvalue problems in bounded domain. You get this pair, so which now I have denoted like Vn lambda star n. So this is something you solve in the ball of radius 0, that is Bn, and you get this Dirichlet eigenpair, and so as I said, that this increases, and one can prove that this, if it increases, it has to be less than lambda star. So it has to nothing to do with the problem in whole dimension. Now, I choose a ball B such that my L dominates this term. So I have this term C. I knew that L grows faster than C, and this is a finite quantity, L is incompact, it grows at infinity, so I can definitely find a ball B, okay? So you take a ball B such that L dominates C minus lambda star, okay, for all large n, lambda n star for all large n. And so this is my ball B, and let's see what happens outside the ball, okay? And it's some simple calculation. You can write down this, you subtract the equations from that you get, you subtract this guy from this guy, and you actually just write down the simple calculations. It gives me this equation that if I subtract, I get something like that. But what is interesting about it is the following. Now my Vn, if you look at my Vn has to vanish on the boundary, on the complement. But whereas my Lyapunov function is positive, so I can lift my function up to Vn, because I can multiply with a constant, it will go up. And for some kappa, it will go totally above my Vn. So on the other hand, what I've done is I multiplied Vn with a kappa and lowered the function, okay? I have forced the function, I choose a kappa and such that Vn touches phi from below. I mean, it's a technical part, but that's the first approach to this problem to solve the eigenvalue problem in unbounded domain. So I have lifted my Vn in such a fashion that it touches V from below inside Bn. So this is my Bn, okay, inside the ball. And then what we observed is that under this condition, the point where it touches has to be inside B. It cannot be outside. So this is crucial, that I take a kappa n, multiply with Vn, and this is less than equal to this, and this guy is exactly equal to this Lyapunov function at some point, and that point must lie inside V. It cannot be outside, and that follows from something called strong maximum principle. I'm not getting there, but it follows from strong maximum principle. Now, I know now so let's say if I scale all my Vn by this guy, so I multiply all my Dirichlet eigenfunction by a parameter kappa n, now I know all my eigenfunction has to lie below V. Now, if I pass limit, there is at least one point that should touch this guy inside this set. So there is one point where it is non-zero, and that point is in the finite domain. And the rest, I don't even know what happens outside the compact set. It is non-negative, but at least one point where it is positive. So that information I have. And with this information, we can again apply what is called maximum principle to prove the limit is non-zero, and it's a strictly positive function. That's the trick to bypass Harnack using a barrier function. Okay, so this is what is done here, but to make, to go back, because at the end of the day, I also need Ascala-Arzeli to pass to the limit. So, and Ascala-Arzeli boils down to the fact that Vn should have supreme unbounded, which is more or less like Harnack, but it's not exactly Harnack, it's called the modified Harnack, because I have this extra term here, which also saves me. I can just pass to the limit. And that gives me this equation. So at the end, I get a solution to this problem in all of Rn. Now, it still has, there are questions that still not answered here, or we have not been able to answer, that whether can I characterize that as a principal eigenvalue. The same, the one we have for the local case, can a similar characterization be possible here? Or if I take any other beta which is bigger than this lambda, whether this equation has a solution. Those things are not yet known, because those proof actually uses Harnack inequality. The principle of this proof relies on the Harnack inequality, which is not true in this case. So far we don't know whether such property still holds or not, but this is something ongoing, so we are trying to explore those possibilities, that how much of the theory that is true for the local case can be developed in this non-local case and what is not true in this setting. But still we have to answer this part actually, because now we have some eigenvalue and the limiting process has already showed us that this is true, and we have to prove that they are equal, okay? And so with the paper that we have with Ari and Subhamai, we did it using two-state process or Dupes transformation, but which again is a big difficult thing. If you do a log transformation of this solution V, the non-local term gets messy because it doesn't preserve that particular form, because you'd have to take log inside the integration, which doesn't work nicely. So two-state process business does not work here. So we had to put some different kind of argument to justify that the limit we get is exactly equal to that one. Okay, that's what I just said. The approach we used for local setting does not quite work in the non-local setting. Okay, now another, so this is the full theorem I wanted to just display. So we get, we could show that the eigenvalue problem can be solved, and this is a nonlinear eigenvalue problem because we have a minimum here. And if you pick any minimizing selector, it's going to be optimal control. If you pick any stationary or Markov optimal control, it has to be a minimizing selector. And this solution here is unique in this class. Okay, if you take any V in this class, it's unique up to a multiplicative constant. So to take care of that, I freeze this value at 0, which is 1. So all this can be shown. There is another variant of the problem, which is the maximization problem. So instead of looking at the minimum, you look at the maximum of the same cost, and they are not equivalent. It's not that you multiply with a minus and you get a minimization problem, because it's a nonlinear problem, so it doesn't work that way. So for the maximization problem, if you, what we did actually, we removed the Lyapunov, so we don't need barrier anymore. So this is something interesting, that when you were doing maximization problem, we don't need to construct the barrier. There is some intrinsic behavior of the solutions of the Dirichlet problems, Dirichlet solutions in the maximization problem that helps us to pass the limit. We don't need to, we can show that this solution cannot, the supremum has to stay in a compact set, it cannot go away. This happens for the maximization problem, not for the minimization problem. That's something interesting. And to have a stability, we need something, a near monotonicity condition, so that it will not take the mass to infinity. So this is something classical in ergodic control. But still, what remained an open problem is if I'm looking at the minimization problem, but under near monotonicity criteria. So we want to see that if we want to look at the minimization problem, but if we remove the stability hypothesis, which actually helped us to also construct the barrier. So if you remove the stability hypothesis, you want to study the minimization problem. Can this problem be answered using all this spectral theory or eigenvalue problem? So that remained still, I don't know. So we are trying to explore this area. What can be said, and how much of the theory for eigenvalue problem be developed for non-local operators. Okay, thank you.